All right, so let's talk about how to implement Kruskal's algorithm. So I've drawn here this example graph we've been using, and this is before I've started running Kruskal's algorithm, so none of these edges have been picked yet. So we can imagine that all the vertices are just like by themselves, right? They're not connected to anything else yet because we haven't picked any edges. So I've indicated that by just drawing these little circles around each vertex. So each vertex is just kind of this isolated thing by itself. It's not connected to anything. And so, right, we sort the edges from smallest to biggest, and we're going to go through them in that order. And so, like, we look at edge 1 first, and the point is, it doesn't matter whether we've seen these vertices before or not, but the point is that they are not connected to each other at all. Right? If they were already connected, then we don't want to add that new edge because it would make a cycle. But obviously the first edge, that's never going to happen. So we can in fact pick this edge, and what that does is it joins those two vertices. They used to be their own independent things, and now they're joined into one connected component. So I'm going to kind of erase this and kind of draw this, right? Imagine kind of like it's become this big blob that's got two vertices that are connected. And as we keep adding more edges, we're going to connect more and more things together, right? So the next edge is 2. I look here, so this vertex is in some blob here. This vertex is in its own individual blob, but they're not connected already. And so it's okay to add this edge that will make a cycle. So we're gonna add this edge, and again, we join these together. So now I've got a bigger connected component, right? So now A, F, and E are all in the same connected component. All the other vertices are still in one by themselves. So we'll keep doing this one more. So again, this edge is okay. I connect this B to this existing big component. The next edge 4, right, is going to be here, and that's okay too. That's going to connect these two vertices into a component. 5 is going to be okay. 6 is going to be okay. So I can do both of them at the same time. So do that one, do that one. All right, so now it kind of looks like this. Okay, so now I've got, right at this point I've got, this is one big connected component. This vertex is by itself, this is by itself, this is a connected component. The next edge that I look at, right, is this edge up here, 7. And the thing that I can notice now is, look, the endpoints of 7 are F and G. F and G are already in the same connected component. That means there's already a path somewhere from F to G through edges that we've picked. So I don't want to add this edge because it would complete a cycle. And the thing is, I don't actually care what the path is. It doesn't matter, right? As long as there's some way to get from F to G, I don't want to add that new edge because it would make a cycle. So we do not add that edge, right? And then, and notice at each step, right? At each step, if I don't pick an edge, then fine, nothing changes. If I do pick an edge, then it's going to take two connected components that used to be separate and glue them into one connected component, right? So each step, the number of components is going down by 1. And this makes sense, right? Because we start with n components, and if every step we add one edge and we decrease the number of components by 1, right, then after we do that n minus 1 times, we're going to have exactly one giant component. And that makes sense because we already know that there's supposed to be n minus 1 edges in a tree. So if I add 8, it's going to be like that. We're down to only 3 components. 9 is okay. It's going to join these two things. And then 10, also okay, right? 10 is joining this giant component to this giant component. And that's the last thing. So we can stop early at this point if we want. Right? But we could also, we could keep going and say, oh, look, 11, the endpoints are already in the same component, so don't add that. Oh, 12, the endpoints are already in the same component, don't add that. I mean, that's going to be the same for all these edges. Okay, but this is in general how we think about Kruskal's algorithm working. And the point is, to make it run fast, we need a way to keep track of what are the connected components right now. And given two vertices, are they in the same connected component or not? Again, we don't care what the path is between them, but we do care, whether they are in the same blob or not. So we're really just keeping track of kind of sets of vertices, right? As long as I know, oh, these 5 vertices are all connected to each other, and these 3 vertices are all connected to each other. Given 2 vertices, I say, are they the same set or not? If they are, then I don't add the edge. And if they're in different sets, then I add the edge and I union the sets together, and now I have a bigger set, right? So all that matters is which vertices are in the same set, not how are they connected. And so there's really 3 operations that we need. And the operations are so we need one I'll call make sets, and it's going to just create n independent singleton sets, and we'll just say, by convention, containing or I'll just say labeled, not containing, whatever, containing, 0 through n minus 1. Now, if we want, we could label them some other way, but we could always kind of have a dictionary to translate between numbers from 0 to n minus 1, and, like in this case, this graph has letters. So we could just set up a little dictionary that maps between the letters and numbers from 0 to n minus 1. So we're just going to talk about this data structure as if it always is just working with numbers from 0 to n minus 1. But we can easily put a little dictionary on the side to translate to whatever our vertices actually are if we need to. Right, and so this, at the start of this, right, each vertex was in its own little set by itself. And so that's what that make sets is going to do. It sets up the initial state. And then we're going to have an operation called find, say find v, which is going to return the name, I'm putting name in quotes, of the set containing v. Okay, so the point is, it doesn't really, I put name in quotes because it doesn't really matter what the name is. The point is that, any 2 vertices in the same set, when I ask for the name of when I do find, I'm going to get the same name, right, because they're in the same set. So in practice, we're going to use, we'll pick one of the vertices in the set as the name of the set, but in such a way that anything in that set will return that one vertex as the name. So we'll kind of pick one vertex as, you are the representative for this whole set, and if we call find on anything else in there, you're going to get that one vertex back. And that means, right, to check whether 2 vertices are in the same set, all we have to do is call find on both and just see whether they're equal or not. If the name we get back is equal, they're in the same set. If we get back unequal things, then they're in different sets. Okay, and finally, right, and again, that find, that's how we check whether we ought to add an end or not. We look at an edge, we have its 2 endpoints, and we call find on both endpoints, and we see, do we get the same thing back? In that case, we should not add the edge because it would make a cycle. Or do we get back different things? That means they're in different connected sets, connected components, so we can add that edge. But then when we add it, right, we need to glue those sets together, and so that's what this last operation is. So union takes 2 vertices, or 2 items, right, and it unions together the sets containing u and v. The sets containing u and v. Okay? So let's see how to rewrite Kruskal's algorithm. Just assuming that we have some kind of data structure that supports these operations, let's rewrite Kruskal's algorithm and see how we would do it in terms of this data structure. Right? We don't yet know how to implement this. I mean, you could probably think of a way that would be not very fast, but we'll talk about that later. Okay, so here's how we're going to implement Kruskal's algorithm. So we take a graph G, and we, of course, we first sort the edges by weight. That part's the same. We're gonna, make an empty set of edges. That's our tree. I'm gonna make I guess, my n is the vertices, so I'll just say, the number of vertices is how many of these singleton sets I'm going to make. And we're just going to assume that, our vertices are labeled 0 through n minus 1 or something. Doesn't really matter. And, right, for each edge, E equals UV, right? And I'm assuming I'm looping through them here in order from smallest to biggest. That's the point of sorting them, right? So for each edge, right, we first check and see if it would make a cycle, which we do by checking if the two vertices are already in the same set, then we don't want to add it. So I guess I want to say if u dot find little u is not equal to u dot find v, right? So if they're not in the same set, then I add the edge E to the tree T, and I union those two things together, right? Because now I've added that edge, and so the sets, the connected components having those vertices are now joined together into one big component. So I'm going to say u dot union u little u and v. This is a big U and that's a little u. Let's see. That's a little confusing. We're calling this U because this thing is called a union find data structure. Or it's either called a disjoint set data structure or a union find data structure. I usually call it union find, so I often use the letter U to stand for one, but you'll see both those terms used. Okay, so how long does this take? And obviously it depends on how long these operations take, so we'll take that into account. So, of course, we already know, right, sorting that by weight takes theta of E log E, which is the same as E log V. Right, this takes constant time, so that's theta 1, which we don't care about. Right, this takes, I don't know, we'll just call it T sub make of V. Right, however long the make sets operation takes. This loop happens E times in the worst case. So this is theta of E times, I'm going to put a bracket here to say, like, this whole thing happens theta of E times, and so what happens in here? Well, this is going to be, here we just call the find operation twice, so it's just 2 times, this takes theta of, well, I'll just say it takes T find V. I mean, really, it takes 2 times that, but we don't care about the 2. Adding E to T, that's constant time, and then this takes T union V. Okay, so the total, if we add all this up, right, it's going to be theta of E log V, plus we don't care about the constant, plus T make V plus E times find plus union. So it's going to be like so E times T find V plus T union v. Okay. Hopefully you can see that. And maybe it's a little hard to read, but so I'll just pronounce it again, just to make sure. So this is theta e log v. That's how long the sorting takes. Right, then however long t make v, that's how long it takes to create the sets in the first place. And right, probably that's just going to take like theta of v time, however we implement it, but it's probably not going to take this long, so that probably doesn't really matter. And then this is theta of e times, so that's a times t find v plus t union v. And right, so here we have e times log v, and here we have e times something, right? And if this whole thing is, for example, v, then this is going to be theta of e times v, which is going to be bigger than e times log v, and the whole thing would just be theta of e times v. But we could already do e times v, where we did the silly way where we just like, instead of using some fancy data structure, we just searched directly to see whether there's a path from one end of each edge to the other end. So ideally, right, if we can find a way to have both of these things, find and union, work in log v time, right, then this whole thing would be e times log v, which would be the same as this part, and so the whole thing would run in e log v. And that would be good, because that would be better than the e times v we came up with the other day. Right, but the point is, like, even if one of these is constant time, say, but if the other one is theta of v, that's no good, because that means the whole thing is going to be too slow. So our goal is to come up with a way to implement this data structure that supports, in particular, the find and union operations in log v time or better. And so that's what we're going to talk about in the next video.